Assalamu alaikum wa rahmatullahi wa barakatuh. In this session, we will be discussing a Fourier series and Fourier transform. So let's begin our lesson plan, and we will start with the Fourier series. So how do we represent a time domain signal in terms of its frequency content, and why do we need to do that? So imagine we have, let's say we have two music notes. This is A of T, and it's periodic, and it has a frequency of 300 Hertz. And this is B of T, and it's also periodic, and it has a frequency of, let's say, 400 Hertz. And these signals are in time, of course. And let's say that we also have some noise. So this is our first noisy signal. Let's say that it's a low frequency noise. Let's say it's about 50 Hertz. And this is N1 of T. And then we have another high frequency noise. And let's say this one is about 600 Hertz. N2. So the signal that we actually hear, or the sound that we actually hear, is a superposition of all of these signals. فحتكون A of T plus B of T, N1T, N2T, all combined into one signal. So it is something that looks like this. Sorry. تكون حاجة عاملة كده. وحتكون برضو periodic, of course. So this graph is not very accurate, but this is the superposition of the signals. So if we want to cancel the noise, if we want to eliminate these two, it's very difficult in time domain. So this is why we resort to the Fourier series and Fourier transform. So in Fourier, if we apply the Fourier series to this signal, we get something that looks like this in frequency, and this is a single-sided spectrum, let's say. And it tells us that, for example, at 50 Hertz, there's a small peak. And this small peak represents this entire waveform in frequency domain. The same thing at 300 Hertz, there's a waveform. And at 400 Hertz. And then we have at 600 Hertz. So if we apply a bandpass filter to this signal, it can attenuate any signal that is outside this range, and we can effectively cancel noise. So this is just one application of the Fourier series, and the signal could be anything. In this example, it was a musical note, but it could be, for example, an ECG signal, sensor readings, or it could even be images in spatial domain. But then if the signal is not periodic, we need to apply the Fourier transform. So the Fourier transform just simply assumes that the signal is periodic, but with a period of infinity. So first, let's go back to the Fourier series and let's look at the representations. There's a trigonometric and exponential representation, and this form is known as the combined harmonic form. And all of them have coefficients and their equations to find them. So these are the equations. The relationships between the coefficients is useful because if we find the trigonometric Fourier series, for example, we don't need to start from the beginning to find the exponential Fourier series. We can just use the relationships. We will see later when we solve the example together. So these are also useful identities. They will come in handy when we want to solve an example or a problem, especially the first, second, and the last one are the most used. And one important thing we should note is that if the signal is real valued, which means it has no complex values, which is 90% of the time, the trigonometric spectrum في الماgnitude and phase بيكون single-sided. هنا بيكون الماgnitude بتاع an square plus bn square under the square root. المهم إنه بيكون بجاي ما في حاجة single sided لأنه summation بيبدأ من 1. في ال complex exponential Fourier series الspectrum بيكون double sided. This is because we have something called conjugate symmetry, which means that ck conjugate is equal to c minus k. Oh, and let's use n because it's more familiar, which means that the magnitude of Cn is equal to the magnitude of C minus n, and also the phase of Cn is equal to minus the phase of C negative n. ده معناه شنو؟ ده معناه إنه الماجنتيود سبيكتروم بيكون even، لأنه هنا مثلا إذا عندنا Cn وهنا C minus n أي قيمة هيكونوا نفس ال value and so on. So it's even symmetric about the y-axis. ده الماجنتيود spectrum. بالنسبة للphase spectrum بيكون odd. So let's say if this is at Cn دي هنا Cn C minus n ده الهايت بتاع البيك، وهنا الابسولوت value بتاع Cn. هنا let's say at the frequency 2f0 minus 2f0 هيكونوا إشاراتهم عكس بعض فبيكون odd. And if this looks like this, then the next one looks like this, and so on. ده الphase spectrum. So let's do the first example and consider the periodic square wave shown in figure 510. Determine the complex exponential Fourier series of xt. We will do it step by step. First, let's write the main formula. X of t two pi over t naught, t لأنه omega naught is 2 pi over t naught. This is what's given by the question. أدانا البيريود t naught. بعدين let's find Cn 1 over t naught, the integral over one period, so let's choose 0 to t naught. Xt exponent negative jn 2 pi over t naught t, which is equal to 1 over t naught. And since the function has only two values, which are a and minus a, we can split the integral into two parts. From 0 to t naught over 2, the value is a, and from t naught over 2 t naught, the value is minus a. Next, we evaluate the integral a over t naught times 1 over negative j n 2 pi over t naught. بعدين exponent jn 2 pi over t naught between the limits a over t naught نفس الحاجة exponent negative jn 2 pi over t naught والlimits. طيب let's substitute the limits. ممكن نجيب دي في النيوميريتور هتكون اتكنسلت, so we can cancel this. So it's a والماينس j برضو ممكن نجيبها في النيوميريتور, so 1 over minus j is positive j, so it's ja هنا 2 pi n. بعدين نعوض limits minus jn 2 pi over t naught times t naught over 2. We cancel minus anything raised to power 0 is 1 minus a over هنا نفس الحاجة, اللهم حتكون negative j 2 pi n. بعدين هنا we substitute minus jn, هنا j حتكون 2 pi n بس التي نوت حتتكنسل, والترم التاني حيكون نفس الأول هنا اللي هي حيكون jn pi negative jn pi. We can factor out this term, so it's ja over 2 pi n big bracket exponent negative jn pi minus 1 minus exponent negative j 2 pi n minus exponent negative j n pi. And then we can add these two terms. So نحطه هنا. بعدين we can use the identity that exponent j n pi is equal to minus 1 to the power of n. So let's work on this side. طيب نعوض بالايدنتيتي. قلنا حتكون JA over 2 pi n 2 minus 1 to the power of n minus 1 تاني minus negative 1 to the power of 2n. Minus 1 to the power of 2n is 1. So this one بكده 1 الترم ده minus 1 حيكون 2. So we can cancel this 2. So it's JA over pi n minus 1 to the power of n minus 1. The Cn. So the complex exponential Fourier series, we just substituted xt is equal to summation from minus infinity to infinity JA over pi n minus 1 to the power of n minus 1 exponent jn 2 pi over t naught t. We can simplify it further by لأنه احنا عندنا هنا term بتاع minus 1 to the power of n. So we can find when n is odd and when n is even, and then we can simplify the summation even further. But in my opinion this is sufficient because we're not testing mathematics knowledge. So let's find when n is even and when n is odd anyway. عندنا قلنا the Cn. You can skip this part. طيب when n is even يعني let's say let n is equal to 2m. So C 2m is going to be JA over pi 2m minus 1 to the power of 2m minus 1. Here minus 1 to the power of 2m, this will be 1. 1 minus 1 is 0. So 0. So كل terms when n is even هتكون 0. طيب when n is odd we let n equal to m plus 1. So C 2m plus 1 هتكون JA to the power of 2m plus 1 يعني minus 1 to the power of 2m minus 1. دي هتكون 1 بعدين minus 1 هتكون minus 2 minus 2aj over pi over 2m plus 1. So summation ممكن نقول إنه Cn هي عبارة عن C 2m plus 1 وممكن نعوض دي في السميشن بداله. So copy paste و xt هتكون summation من m equal minus infinity ل positive infinity دي Cn حقتنا اللي هي Cm2 plus 1 times exponent j 2m plus 1 2 pi over t naught اللي هي omega naught times t. Let's compare it to the final answer. Let's do letter B now. Determine the trigonometric Fourier series of xt. So since we already found the complex exponential Fourier series, we don't need to compute again. We can use the relationships. So a naught is equal to 2c naught 0 أو ممكن نقول بالsymmetry. So a2m plus 1 هتكون c 2m plus 1 plus c minus 2m minus 1 negative 2aj plus pi over pi 2m plus 1 باي نيجاتيف 2m نيجاتيف 1. دي هتكون 0. أو ممكن بس straight away يعني no need to compute it in the first place. It's correct but not يعني we can see from the symmetry that x of t is odd, so we can straight away say that n is equal to 0 for all n because we have odd symmetry. Sorry. بعدين let's find bn. So bn is equal to j c 2m plus 1 minus c minus 2m minus 1. It's going to be j minus 2aj by 2m plus 1 minus 2aj negative pi 2m plus 1. هنا طلعنا الماينس برا, so this is equal to j. هنا minus و minus هيتكنسلوا, هتكون negative 4a pi 2m plus 1. هنا في j برضو, بعدين j و j minus 1 والماينس و minus will cancel by 2m plus 1. دي القوانين اللي استعملناها. بعدين بس نعوض في ال series في ال expansion اللي هو ده copy. طيب ده 0 ده 0, عندنا بس الترم ده اوميجا نوت بتساوي 2 باي over t نوت. والسميشن بيبدأ من n equal 1, لكن احنا عندنا it's only valid when we have n, when we let n to n plus 1. So when n tends to 1, when n tends to 1, m tends to 0. So we just substitute x of t will be equal to the summation from m equals 0 to infinity bn, which is 4a over pi 2m plus 1 في sin n اللي هي 2m plus 1 دي 2m plus 1 times omega naught 2 pi over t naught t. طيب let's also sketch the double-sided spectrum up to the fifth harmonic. So first double-sided spectrum معناته هنشتغل بالcomplex coefficients. C2m plus 1. طيب we know that it's even, يعني we know that كل height هنا is replicated the same value بجاي. We can sketch it against f يعني frequency or angular frequency in hertz or in radians per second. It's up to us. So let's do in hertz. عندنا بس odd frequencies, so احنا شغالين frequency واحنا عندنا omega naught, so حتكون هنا omega naught over 2 pi, هنا 3 omega naught over 2 pi, هنا 5 omega naught over 2 pi, negative 3 omega naught over 2 pi, هنا أول omega naught over 2 pi, negative 3 omega naught over 2 pi, negative 5 omega naught over 2 pi. بعدين نجيب ال values. هنا حتكون C1, هنا حتكون C3, هنا حتكون C5, هنا حتكون C minus 1, C minus 1 حتكون equal to C1, هنا حتكون C minus 3 حتكون equal to C3, ونفس الشيء C minus 5 حتكون equal to C5. ليه؟ لأنه دي real valued signal, فالspectrum حيكون even. So let's find C1 when m is equal to 0. So C1 is equal to negative 2a j. By the way احنا عايزين الماgnitude, so over pi, so it's 2a over pi. لما m equal 1 C3 نجيب الماgnitude حقها, بعدين نعوض m equal 2 تحدينا C5, كده حنكون جبنا up to the fifth harmonic. هنا حتكون 2a over pi, هنا حتكون 2a over 3 pi, هنا 2a over 5 باي. هنا نفس الحاجة، نفس السبكتروم 2a over pi هنا 2a over 5 pi. double-sided magnitude spectrum كده رسمناه. So let's move on to the Fourier transform. So these are the applications of the Fourier transform. In the same way as the Fourier series, it's useful for analyzing the frequency content of signals. It makes signal processing easier, image processing, and solving differential equations as well. This is the Fourier transform pair, and it's for converting between the frequency domain and time domain. The properties to Fourier transform, we're going to use some of them. Actually, we're only going to use 2 of them in the coming example, but all of them I believe are equally important. We just don't have enough time to cover all of them. The Fourier transform pairs for known signals, and I don't believe they should be memorized, lakin we should know how to use them. So first let's do this example on Fourier transform properties. So we are asked to find the Fourier transform of t exponent. So if we look at the differentiation property, in this part we can see that the derivative of the transform, the nth derivative of the transform, introduces t in the time domain, and this is exactly what we want. يعني هنا we have a missing t, so if we differentiate this one time we can get the t that we need. So let's differentiate the Fourier transform. So dt of we differentiate in omega 2 over 1 plus omega square. ممكن نستعمل أي قانون minus 2 omega divided by 1 plus omega square all square. بعدين ده الانفرس Fourier transform حقه 1 plus omega square all square. According to this هيكون minus j t to the power of 1 f of t. So it's minus jt في jt في exponent minus t. طيب بما انه let's copy this. بما انه the Fourier series has the linearity property, we can actually factor out this minus j. ممكن نقول إنه Fourier transform of negative j. يعني let's just take the Fourier transform of both sides just to make it more clear. Fourier transform of minus jt exponent, this is equal to negative 4 omega. كده ممكن ناخد ال negative j to the other side by linearity، لأنه هنا في تكامل وبرضه هنا كان في تكامل. هنا في تكامل كان من minus infinity to infinity حسب القانون يعني، فممكن نطلع ال minus j برا. So the Fourier transform of t بعد ما نطلعها برا ال minus j ممكن نعمل 1 over minus j هنا. So Fourier transform بتاع t exponent minus t is equal to negative 4 omega 1 plus omega square هنا في square all square. Letter B, use the result from A along with the duality property to determine the Fourier transform of this type. It's explicitly asking us to use the duality property and the result from A. So result from A هي دي والduality property خلينا نجيبها, and this is the duality property. So we want to find the Fourier transform of this. معناتها دي هي time domain signal حقتنا, معناتها by duality دي capital F of t بتاعتنا. طيب transform, it says that the Fourier transform of this f of big F of t is 2 pi small f of minus omega. So نرجع للريزلت من part A. دي Fourier transform عادي كان، يعني ما كانت تعملنا في duality property، فدي كانت small f of t حقتنا، ودي كانت big f of omega. عشان نحول ال big f of omega حقتنا ونخليها زي ال f of t، زي ال big f of t that's given in the question, let's first convert the omega to t. So let's make it negative 4tj over 1 plus t square all square. تمام؟ دي كده بقت عندنا big f of t. وعارفين انه الفورير ترانسفورم بتاع البيج f of t حقتنا دي هو حيكون ده السمول f دي لكن بماينس اوميجا، فحيكون هو مضروب في 2 باي، فحيكون 2 باي f minus اوميجا، حيكون 2 باي minus 2 باي اوميجا exponent negative minus absolute value of omega هي نفسها اوميجا. But again نستعمل linearity property. الفورير ترانسفورم بتاع big f of t يعني الفورير ترانسفورم حق 4tj over 1 plus t square all square is equal to this. لكن احنا عايزين من غير الماينس 4j، هنا في ماينس من غير الماينس 4j، so ممكن نطلعها برا ونقسمها بيه هنا. So simply الفورير ترانسفورم بتاع big f of t اللي هي 4t over 1 plus t square all square is going to be negative 2 pi، هنا ما في 4 معلش، هتكون هنا على negative j minus j 2 pi omega exponent negative omega over minus j minus و minus cancel، نرفع ال j فوق برضو تكون negative j كده. Okay, this is the last topic in this session, which is the DTFT and DFT. And so far we only considered continuous time signals, but in reality we mostly use discrete signals, especially for computer processing. So for computer processing we need a signal that's discrete, periodic, finite, and in frequency domain. So we use the DTFT and DFT to achieve this. The DTFT just like a continuous time Fourier transform برضو بيكون continuous في frequency domain وكمان بيكون periodic with a period of 2 pi. So it can achieve a periodicity only, and it can achieve إنه نكون في frequency domain. تمام؟ ده inverse discrete time Fourier transform. So if we sample the discrete time Fourier transform, we can obtain the DFT, which is the discrete Fourier transform. So discrete Fourier transform, what it does is that it selects certain frequencies and evaluates them, namely frequencies del 2 pi k over n. والn ده هو length بتاع discrete signal بيجي من truncation that we do in the beginning. Let's see how this is done. So first we start with a continuous time signal, and this continuous time signal is aperiodic and it's infinite and it's in time domain, of course. This signal cannot be processed by a computer. The computer cannot store infinite amounts of information, so we sample it in time. This is the first sampling. After we sample in time, we obtain the discrete version of the same signal. So it looks like something like this, for example, and now it's in n, but it is still aperiodic and it is still infinite. So this is why we cannot use it with the computer. Next, we have to truncate it to make it finite. So we truncate, which means we choose n samples. Choose n samples. Let's say we have the signal only up to here. Let's say from 0 to n. We are keeping only n samples. وده كله نحن we are still in time domain, by the way. So this is still in discrete time. Now we can apply the DTFT. If we apply the DTFT بنكون بقينا في frequency domain، لكن السبكتروم اللي حيجينا حيكون continuous وحيكون periodic. والبريود حقته كمان حتكون 2 pi. So every 2 pi this shape is going to repeat and so on. And now we are in frequency domain FR omega. So زي ما قلنا حيكون periodic والبريود حقته 2 pi. هنا x exponent j omega is equal to x exponent j omega plus 2 pi. تمام. دي كانت شنو؟ دي كانت a periodic and finite. طيب after this we obtain the DFT. So the DFT is simply we sample the DTFT. So we are now sampling in frequency domain. The first sampling here was in time domain. وينه؟ هنا. The first sampling ده كان in time domain. بعدين the signal is going to inherit the periodicity from the it will inherit periodicity from the DTFT, لكن حتكون بقت discrete discrete و periodic. والperiod حقتها حتكون n لأنه we sample at n equal spaced intervals. So it's going to, I'm not sure if this is accurate, but let's say something like this. كده finally بيكون عندنا signal اللي احنا عايزينها, which is periodic, finite, discrete, and in frequency domain. This is why it's important to use a DTFT and DFT. This is another example, but I don't think we have enough time to do it, so I will attach the solution with a slide. And that's all. This is a summary for everything we just discussed, and thank you for watching.